Today we're going to talk about some of the experiences that we have had with Vega, the car that we're building, and then the electric vehicle chargers that we're developing, so that I can give my thoughts on and talk to you about the challenges that we have faced when trying to do prototyping to production level software, hardware, and whatnot. Hopefully I can focus my slides here more on the software side of things. We do have a lot of firmware and a lot of backend software as well, but you will have to get a taste of the hardware problems that we have had. Okay, so prototype to production. What does that mean? I have seen a lot of prototypes that are being developed at universities, at hackathons, you name it. There's so many things that we develop as prototypes, but only a few of them goes to the next step in terms of getting into production, in terms of having actual customers who wants to buy it, sometimes having customers who want to even get it for free. So what's the gap? Why is it so hard to get prototypes into production level? So this is what I want to discuss today. Hopefully we can exchange ideas and not just me speaking, so that way I get to learn from your the work that you all do as well. Okay, so just to give you a brief description about who we are. I'm part of a larger company called CodeGen International. It's one of the largest software companies in Sri Lanka. We have about 540 employees now. Mostly focused in the travel sector, in travel-related software for booking and whatnot. Our flagship product is called TravelBox, which is sold to big airliners, cruise liners, and so on. So about 5 years ago, our CEO wanted to get into mechatronics, electronics, and other things, not just software. So we thought of building an electric supercar. We wanted to do something that was never done in Sri Lanka before, something that needed multidisciplinaries to come together to showcase that we can do cool things in Sri Lanka, and that people, especially young graduates, don't have to leave Sri Lanka to do bigger and better things. At the time when we started, we had no idea about how to build an electric car or a supercar for that reason, and so our timelines were really off. Our budgets were really off. We thought we could get this done in about a year's time. It's been 4.5 years now since we have started work. We are now in the final stages of doing the paint work and getting it ready for a soft launch. So it's been a long run for us. It's been a lot of learning, especially trying to get our prototype circuits, prototype devices, mechanical devices, the software into a production level. So so moving on. This is some text that I stole from the internet today. So from idea to a proof of concept, to functional prototype, to public launch, and then production, and ongoing support. All those steps have a lot of pitfalls, especially the last few ones. It's easy to do the public launch because you can showcase what really works and you don't have to showcase all of the other problems. But going into production and supporting the customers is the biggest problem, biggest challenge. It's more of a problem if your software is not up to speed, not up to date, not working as you would need. So in a very theoretical manner, first, a product development life cycle looks something like this. There is a prototype. You have to design it to be a production level. You do more development, then a lot of testing. Then you do performance engineering to reduce the costs, make it smaller, make it lighter, make it work faster, or you can handle more load on a server system. Then you do deployment. You need to do support, a lot of maintenance work. And then to do continuous innovation, you have to do more research and innovation to push that product forward. So this is somewhat the more traditional or the more textbook way of thinking about product development life cycle, and then looking at prototype to production steps per se. So if you look up, for hardware especially, there is a lot of manufacturing costs involved. You need a bill of materials, which is the cost of every component. You need to have a minimum order quantity, because some of the factories don't make 2 or 3 devices for you. They'll make about 100 or 1,000. Then once you are ready to do a purchase order, then you need to have investment to pay for that, and then have the sales and marketing ready to kind of deliver that to the next level, start selling it, start marketing it, and pushing it to the people. Sorry, these are all hardware, but when you make a device, say a coffee cup or something, there is a tooling cost involved. Tooling cost is, to make a prototype, you need to make a mold that you have to CNC maybe using aluminum or steel, and these have a big cost. Then you have to make sure the quality of the product is good, and then worry about packaging, storage, and installation. So some of these don't apply for software, but some of them do. Quality is a thing that you all need to worry about. Our electric vehicle chargers have a lot of software. There is a firmware layer on the microcontrollers. Then we have an IoT layer that takes the data and pushes into a backend server. Then on a cloud-based system, we have a lot of software that runs to manage the smart charging network. So all of that has to work to get the charger to start. It doesn't matter if your hardware is working. If your smart card doesn't get authenticated from the backend server, the user cannot charge the vehicle. So early on, there was a lot of customers that we struggled to get them to charge their cars. They would go to Kandy or Anuradhapura and figure out that our charger doesn't connect to the internet. So we had to send somebody sometimes to get the vehicles charged. So now we are very focused on being able to do remote debugging, remote capabilities, so that you don't have to travel to all of these far-off places, but can manage the entire thing from a Colombo office. About the car. The idea, as I told you before, was to build something that was never done in Sri Lanka before. We looked at building a laptop, mobile phones at the time, because those are all cool, nifty things as well. But a car is something that everybody connects to. Everybody uses some sort of transportation in their lives on a daily basis. So we thought of building an electric car. Now, 4 years ago or 4.5 years ago, electric cars were just coming into the market. Tesla was just getting into the game. Leafs were all built in the 2012-13 models. So it was a good time to get into the electric vehicle scene. Of course, the market has moved rapidly in the last 4 years. So whatever we planned for in 2013 is now getting obsolete. So we have been trying to do changes to our design to kind of keep up with the evolving market. So this picture here is a 3D printed vehicle that we printed in 2014, just after we got the hand-drawn drawings of the vehicle from a guy called Dash Gunaratna, who designed the vehicle for us. And we did a 3D print to see what it looks like, how does it look, what are the kind of the problems, things like that. So in terms of developing prototypes, using these rapid development tools is now used everywhere. It's very cheap to do 3D prints when you compare it with doing actual models. So it's the way to go, so that you know what it looks like. You can touch it, feel it, turn it around, look at the issues with it, and kind of figure out what you want to do with it. So out of that idea, we wanted to see what we need to do to bring that to life. So This, I think, is the most important aspect of our project here is the people. Without these young, passionate group of guys and girls, I don't think we'll be able to do any of this work. So our success is really based on these guys here, and some of them are not on this picture. We, as a team, practice a very flat hierarchy. There are no middle managers. We hardly practice any manager positions. Everybody has the same voice. Interns who come in, they have the same voice, so that everybody can give out ideas, be able to criticize others to get the best out of them, so that you ask more questions and make sure that you're doing the best thing at the right time. So this is, it's easier to say it, but very difficult in practice, because we are used to in a culture of hierarchy. When some of these guys come out of the universities, they have to call somebody Ayya or Akka or Sir or Mr. for some reason. So when I tell them to call me by my name, it's a very big struggle for them. I've been struggling with some of these guys even now. When they joined, I would say, don't call me sir, call me Beshan. And then they wouldn't tell my name, because then it would make them feel bad. So they would just say, not say out a name to get started, to start the conversation. So they struggle with that now as well. So I think those artificial boundaries make it difficult to innovate very quickly, to kind of get the best out of them. So we try to keep that to a minimum. And also we have people who have not done their O-levels or A-levels, who are very creative, but who are part of our team. There was one guy who came to volunteer 1 day per week, because he used to work at his uncle's garage 6 days a week. He gets 1 day off. And on this day off, he would come in the bus, work with us, and then go back to his grandmother's place where he was staying. So he would do this for about 1 year or so. Then we decided to hire him. So he's now an integral part of our team. Without those kind of opportunities, I don't think they would be able to shine anywhere. There's so many of these youngsters out there who are who have a lot of talent in this country, but who doesn't have a platform or a place to show it off or to try it out. So we are blessed to have people like that as part of our team too. That's our team. They are very dedicated, and I think the fact that they work on a supercar makes them a lot more motivated than maybe some other positions out there. So this is how we began about 4.5 years ago. We didn't have a place to start, so we built this car at my garage at home in Dehiwala. So we started building this chassis, which is a chassis for the Lotus 1967 Lotus vehicle, just to see how we could do a chassis, how whether we can weld it properly, or just to get an idea about what we wanted to do. So this is how we started. It's a very humble beginning for us. We go back to this picture quite often, just to make sure that everybody knows how we started, so that we kind of ground ourselves on the difficulties of doing a prototype or a supercar that to be developed in Sri Lanka, given the kind of the problems, the resources and constraints that we have. So there was a lot of research that we did. Again, this is one of those Lotus vehicles that we looked at to understand and study how chassis works, what we could do to learn from them to kind of push the technology forward. So you might think that this looks like a very old car, what are these guys doing research in this vehicle? But the chassis of this vehicle was used in the 2000 Lotus as well. So it's a very old design, but it's a very modern, the mathematics, the fundamentals are still the same. We studied so many other vehicles to get started. As far as doing research, this is one of the easiest things that we can do from Sri Lanka. Our 4G connections are good enough to download a lot of internet things. Everything is on YouTube and Google nowadays, so there is no reason or no excuse for to understanding how others do things. If you do an image search for anything, you get thousands and thousands of hits. So doing research has become a lot more simpler than when you had to go to a library or you had to go to IEEE website and download a large document and read it through, trying to find out what they did. So research is something that we spend a lot of time on, about 2 years per se, I think. We're still doing a lot of research on certain things. Then came the time to do simulations. So before any of the metalwork was done, any of the designs were done, we went through a lot of simulations trying to understand how to do things properly. So we borrowed university computing resources at Moratuwa to run some of these extensive simulation programs, trying to understand. In this picture, it shows the kind of the structural forces on the chassis to design it properly with the right amount of material and strength to get the best out of building a chassis like this. So we did this kind of simulation, FEV, wind tunnel testing you can do, stressors, dynamic testing. There's so many simulations that you can run now. So any device that you build, even if it's a small desktop device, you can run thermal simulations to see how the temperature affects it, what kind of airflow you need on a circuit board, or how things move in a dynamic environment as well. Then a lot of modeling as well. So every component on this car is first modeled in a computing environment. So we model every weld, every bolt nut that goes on, so that you exactly know how things go, how things fit. And if there are any problems related to actually manufacturing something like this. So this is all done by my team as well. None of us had automobile engineering experience before. So this was all new. So all of this took time to kind of develop and get it to a certain stage. So that's the chassis about 3 years ago, I think. This is where we started building the chassis. It's a space frame chassis made out of mild steel. These kind of chassis are being used in a limited number of manufactured vehicles. At this point of the build, the square aluminum thing in the back here is the gearbox that we designed in Sri Lanka. And at this point, it was a rear-wheel drive car. Both motors were at the back. So 2 years into this, we decided that this was not going to be good enough with the moving market. Like I said before, the market was moving very quickly. Tesla was doing new models. Leaf was getting into the game. A company called Rimac in Croatia was building this $1 million car. So we decided to change the design to do all-wheel drive. So that would give you more accelerated power when you need. So that was one of the biggest design changes that we had to do in flight coming up to now. So after about 3 years or so, we got the chance to do the first drive. This was a big moment for us because building a prototype, building a car especially, if you can't drive it, it's very boring. So 3 years of doing it just to get to the point where you can start driving it. So this was a big moment for us because it meant that most of the components were in place, so that we had the design within our reach to kind of get it done. One thing I must say that when Tesla or even Rimac, when they built their first cars, all of the electronics were brought in from other companies. Companies like Bosch, Siemens, they have the battery packs, the motor controllers, and the battery software that they can just buy and integrate with their vehicle. But we chose a different route when we started this program to make all of that by ourselves, which meant a lot more time, a lot more expertise we needed to build, so that you know how to run, do a motor controller, know how to run the software needed to do center console touch screen software, the instrument cluster software, and overall vehicle controlling software as well. So it was a lot more work than what we started with. So the next video will show you when we first drove the vehicle, which I must say was a big deal for us, especially to know that we can actually drive it. So those motor controllers at the back, the 2 units are, our first or second prototype. It had a smaller battery pack at this time to get everything tested. Was our first drive. Again, this was at very early stages of the prototype. The devices were not, finalized, so there were a lot of bugs and other issues that came with this kind of a version. You can see the front wheels are not powered by this time. The motors were all in the back. So talking about prototypes, so this is the first motor controller that we built. You can see most of the components are outside the casing that we built for it. All the wires are all over the place. The software ran in a big old computer, and the controllers were all just sitting outside. Talking more about prototypes, even with our software, I'm trying to get it to be focused on software, but what we practice now from this learning is that we need to go through 3 prototypes to build the final one. The first version will just be a big old thing with just trying to get the proof of concept going. Second, we try to put it into a smaller package as well as make it more reliable. And by the third one, we try to bring it to a place where it can be manufactured. Even with the software, I think it's the same now. Whenever we write a new set of code for something, the first version is always just dummy functions all over the place, just to make sure that the communication works, that you're not worried about performances, you're not worried about all of the features. You just want to get the most fundamental things going. By the second one, you want to make sure that at least about 90% of your functions are done, that you're able to now do remote debugging and be able to collect statistics. So this was one of the 2 items that we never practiced early on. I think might be useful for the software guys here. Is that without being able to do active debugging while it's being used in a field environment, we believe that it's very difficult to innovate and jump quickly. You have to know how things go wrong, what are the bugs, why are people having problems trying to use your software, even with your hardware. So we have made a lot of time and effort to capture those, maybe using IoT or maybe using socket functions with a backend server to communicate and give across, more data extraction capability into your hands. So we very recently we built a software called Deep Dive, which is used in our electric vehicle chargers now to get the debug information out in real time. Because sometimes when people use their vehicles to charge on our chargers, sometimes they get errors. Rarely happens, but it happens. So we want to know why. We want to know what is it that causes that particular car to have an error. So there is no way for us to sit next to a charger and wait for that customer to come. So we build this software that in real time extracts the important messages, summarizes it, and captures it into a backend MySQL database. Then we use AI algorithms to run on top of that, to kind of use that data and figure out what's going on. What are the data or parameters that correlate to each other to see what happens. So we look at the microcontroller load at that time, the temperatures. We look at how many processors were running at when the error happened, to see if there is any conflict going on. If memory was low, was it the serial bus, was there a power glitch, things like that. So using AI, you are able to now correlate things on its own, be able to be intelligently look for answers that you would normally not see when you do just statistical analysis, for example. So this is something that we've been spending a lot of time on, because nowadays AI is very easy to do. You get your data together and you put it to some service like Microsoft or AWS, and out you get summarized data. So this is something that we've been pushing for our products. So this is what the second prototype looks like. What you saw on the vehicle. All of the components now sit within the enclosure. It's mostly working. Sometimes it doesn't. And you're able to do debugging and get data out of it. By this time, it wouldn't fail quite often, but it would sometimes. And it fails. These components go out with a bang and makes a loud explosion. So it's always heartbreaking when it burns, and it always burns when my CEO drives it. So it's always not a good day when things go bad. So our third prototype, which is on the car right now, looks something like this. As you can see, all of the components are integrated into the PCBs. The microcontrollers have their place. Things look much neater. Everything is in a safer enclosure. So now you're getting closer to that production level device. So this is where we think like you need about 3. Actually, for this motor controller, you need to go to another level as well. Even with this one, you can't go into production right now because of a lot of reasons. So we are now looking at a 4th generation to kind of make it production ready. But you can see how things are moving forward from this to something like this, and then it looks much neater and looks like a real product that that's in the market out there. So by this time, again, on the software side, you are able to now get real-time data out of this. We built using a wireless device that I forgot its name, able to get data out of the car into a laptop in real time, so that you don't have to sit on the car to look at the problems. You can sit in your office and then be able to in real time see what the car is doing, what kind of temperatures, what kind of performance characteristics that you're getting. So same kind of a thing for the battery packs as well. This is our first prototype of the battery. What you see here are the battery cells. They had these cooling pipes to cool each battery cell. This is how we started. Again, all of the circuits are outside and the wires are all hanging all over the place. It sure doesn't look like a battery pack at this point. When it continuously got better, we started putting 2 cold plates, two plates on either side to do all of the cooling. and the circuits were also built in to the device itself, so that it looks much better. Even with vibration and heating, it would still work. But still, it's not production ready. You couldn't move this into a vehicle at this point. So right now our battery packs look something like this. It will have a cover, but all of the cells are integrated. The cooling happens on these two sides, and there are safety devices built in case of an accident or in case of a short circuit. The battery can disconnect on its own, so that you don't have big fires and explosions on the vehicle. So a lot of thinking and research has gone into getting to a stage like this, and a lot of burned batteries to get to this stage as well. So again, this is still not done. There's still a lot more work to do, but it's good enough for the vehicle for the time being. Then at this point in time, we were ready to do a speed test of the car. Maradana. We did the test at night for clearly good reasons. 100 kilometers per hour. So that was a big achievement for us. Some of the Ferraris and Lamborghinis are in that range. The early Teslas was at 3.2 seconds. Right now they do 2.8. The Rimac was also in that range. So if you look at the electric cars, we are in the top, 20 or 30 vehicles in the world. So this was a huge achievement for us. So now we want to get under 3 seconds as well once the car is all completed. Interestingly, they put a speed bump now on that road, so now we can't do this test anymore. So that's mostly about the car. Now I want to quickly talk about chargeNET, our smart charging network. There's more software in this, I hope. So what we build out of this team and our expertise that we have gathered is a smart charging network of electric vehicle chargers. We have about 80 chargers now around the country to cater for our electric car customers. And these are all IoT devices. So all of them have internet capability. They talk to a backend server. We give services like a smart RFID card. They can turn the charger on and off with a mobile application as well. So a lot of features like that. If you look at worldwide networks like that, there's a number of companies like this in Europe and US and so on. But they're very expensive. So we have we have developed a cost-effective solution here. So out of that, we won in 2017 United Nations World Summit Award in Vienna for our EV chargers. So our architecture looks something like this. The users would connect to the charger. There's IoT server. There is a cloud-based backend server running on Amazon. Then there is a connectivity server just for the mobile phones. And then also for the front-end side, there is a web application that or a website that you can log in and make payments, top up your account with using your Visa or MasterCard so that you can use it for anytime you want. Early on, about 2 years ago when we started this, our software was not ready at all, but we went ahead with providing this service because there was nobody else doing that. So then we went through a whole phase of re-engineering the software and hardware to kind of be able to do 24/7 operation. So this is where we moved from prototype to production, where running something for 10 minutes, a single click or one RFID tab, it would work, but it would never work in a 12-hour setting. So moving that to a 24-hour device was very hard for us. There was a lot of learning, a lot of mistakes, trying to get that done properly. I think early on we were very focused on the cost side of things, trying to minimize the costs, trying to bring down, even if it's a server, we would not spend a lot on the server performance, trying to see how to do it in the cheapest way. But what we learned was that in prototypes, that is the wrong way to go. If you are focused on costs and prices at that moment, then you are too slow, you are not doing the proper things to build new technology. What we are doing now is to spend more upfront on the prototypes, use additional resources if you have to. If it's a waste, it's okay. So that if you are going to fail, we are okay with failing quickly rather than failing slowly. That was a big learning for us, and I think that's a big turning point in the stuff that we do. So this is what our mobile application looks like. This is currently on Android only. We are still working on iOS. And that's our fast charger right now. So this device is completely built in Sri Lanka, from housing to software to everything. Of course, things like LCD, we buy it. This is now built as something that can be manufactured easily and readily. Getting these rounded corners, for example, in Sri Lanka is very hard because the companies here are not used to it. They are mostly building things for electrical panels or for Mobitel or something, that you have telephone boxes out there. That doesn't really need a look and feel to it. So trying to get them to change their mindset to build something like this is also very difficult. It's been a very big challenge to get companies on board to do things like that, or to get the material that you need. And even our tax structures are not built to innovate in Sri Lanka. For example, if you buy a charger from China, you can bring it tax-free. So only NBT or some other thing gets charged on you. But if you were to buy the components individually to build your own electric vehicle charger here, then all those components gets taxed at 35%. It's easier to just bring it in rather than build it here, which is a crying shame, right? So we've been talking to a lot of governments officials now, trying to change their mind to kind of see the bigger picture and make changes, because the electronic components that you buy in this country is such a small amount, right? They're used mostly for TV repairs or phone repairs, radios and whatnot. So taxing that is just a pointless thing. That's our another slower charger that we have. So again, this was our first prototype. It was bigger than a fridge. It looked very ugly. It was very heavy, and it didn't really work the way we want to. So then we thought of designing something like this. We actually made one of these and figured out that this was a bad idea. To service this machine, you had to dismantle the entire thing. It would take about 3 days to change a component. It was very expensive to build, so this was a giant mistake going forward. Now our design obviously looks more like this, where the 2 doors open and you can get into the components inside, so it's easier to fix, easier to put new software and do any changes. Apart from that, we work on EV conversions to put electric drivetrains into old cars or even new cars to convert them from petrol or diesel into electric vehicles. We do third-party design work for other companies now. So this prototype to production hardship, we try to help other companies to kind of jump that bridge by giving some of our expertise in getting into production level hardware, software, and things like that. So we have a number of clients that we work with. Finally, we work on AI-based agriculture technologies now. We have a greenhouse in Maradana that we put in new technology, new software into the agriculture field. So this is the billion-dollar thing that's coming up in the next few years. How to increase your food supply, how to have safe food supply for the things that we consume. By 2030, they say that our food production has to increase by 70% worldwide, which for developing countries like us means we have to double our food output, double it. Can you imagine? Cities are growing larger, your growing areas are becoming smaller and smaller, but we still have to double our food output, our agriculture output to feed our people, which means a lot of work has to go in now to make sure that we can hit those goals. So if you look up agriculture technologies, there's a lot of need for new software and new hardware, especially software for agriculture management and so on. So something to think about. So those are all my slides. I think my time is getting there as well. Now, if you all have any questions, I would love to hear, or comments, or even any questions that you wanted to ask about what we do. So over to you. Range of the car. We have designed it for 240 kilometers. We haven't driven that far yet. We have only done about 30 kilometers or so. Once the body is done, we will drive it to far off places and see how it goes. Yeah, so right now it does not have ABS. It's a very conventional braking system now. We didn't want to go into all of those things at once because then we would never get this prototype done. So we don't have airbags, but we have a 5-point harness, just like a racing car, so that you have the kind of the safety features. But we have done a lot of crash testing in a simulation mode, so we know that our chassis can handle that kind of forces. Good question. Yes. Price really depends on what people want to pay for an exotic car like this. The Rimac 1 car that they build in Croatia, again a tourism-based country. They sell it at $1.5 million each for the Middle Eastern market. So we are looking at a market like that, a very niche market for this kind of a very high performance car. But we are working on smaller cars, smaller three-wheelers now, partnering with a Japanese company as well to kind of bring more cheaper vehicles out there so that we can build things here in Sri Lanka rather than having to bring everything overseas. Very good. So thank you very much for participating, and thank you so much.